Okay, hi everyone. Today we have the pleasure to welcome Francesco Di Filippo for our seminar. Francesco is from Goethe University in Frankfurt, and he's going to talk about towards a non-singular paradigm for black hole physics. Okay. So thanks a lot for being here. Please feel free to ask questions during the talk, and there will be also time at the end. So please, you have the floor.
Okay, thank you very much, both for the introduction, especially for taking such a good care of us in these 2 weeks. I'm having a great time in a way. And yeah, so I'm going to talk about, I'm going to discuss what it means with the non-singular paradigm in we call physics. And let me just start in some brief introduction, and I will not spend much time because in the introduction just saying that we have a great theory to describe the gravitational interaction, which is general relativity. This thing is being recorded. Yes. Okay. Oh, and yeah, which is theory very elegant from the formal point of view, and also very successful from the experimental point of view, as we all know, but we also know that the theory emits its own limitations. And, in particular, today I'm going to focus about the results, the result following the series of theorems starting from Bell's singularity theorem, telling us that generically within black holes there will be a loss of predictability of the theory. And I would argue that we need a formal framework to study this problem. Even though, I mean, there are some easy ways to get rid of the solution, and just to say, okay, this is going to happen within the element horizon, so it's going to be a causal disconnecting for any observer outside the core, and so whatever is going to happen, it's not going to influence us. And it's probably maybe sometimes I talk with people and they have this point of view, and it's a problem worth studying, but I would argue that it's still interesting to be just to have a framework for this problem. And this talk is going to be based on this paper with several authors. This paper was the result of a meeting in Trieste last November, in which we tried exactly to address this topic and put some order in what are the open questions and where should be working forward. And in particular, we're going to also discuss some. I mean, this is going to give us the structure of the talk, but then we will enter into the details of some results that they will obtain, especially in collaboration with these people, the organizers of this event.
Francesco, today there was a similar paper as an outcome of a similar conference.
Okay.
And actually, one of the authors was active. So I don't know if you have time to
I didn't check ahead yet.
I would like to know, well, the conclusions are similar.
Okay, I didn't check ahead then today.
Okay.
They didn't know. But it's good to know.
Or maybe after he's alive. I don't know what I can make a comment about that.
Okay, that's great. So let's start from some basic motivation, and I think one of the motivation and the reason why we think we should care can also come from some lesson that we can learn from general gravity. And so let's do this mental experiment. Let's just imagine that we live in a region of the universe in which we have no access to high energy particles, no access to strong gravity phenomena. So in a region of the universe where gravity is a great approximation of the theory of gravity, which seems to be the case of what's going on with the general relativity. We don't have access to the theory of black holes, so we can make the big bunch of gravity. GR seems to be a great description of the theory of gravity. And the question is, should we accept this impossibility of physics, of probing physics beyond Newton? And the answer, of course, we know is no. And one of the reasons is gravitational waves. Gravitational waves is one effect that cannot be predicted within the theory of Newton. And then it also propagates in regional space-time where Newtonian gravity works very well. I mean, we can detect them on Earth, and even though, of course, the origin of this phenomenon is where the theory breaks down. But what I want to say is that this is a qualitative phenomenon. It cannot be predicted in the theory, and it can propagate even in regions where there are no strong gravity phenomena. So I just want to argue that maybe we can keep an open mind and do the same study. What can be the modifications into these effects that we know must be present within black holes, and see if there is something new qualitative in the future. And maybe yes, maybe no, but what I'm going to do today is something way more modest, trying to understand how to address this problem, like what type of framework we can use to discuss it, and these kind of things. I keep pressing the wrong direction. So I mentioned that this paper is based on the outcome of this whole workshop. And in particular, the workshop was organized in a way that we introduced what are in our opinion, the organizer, the main open questions in the field. And we had a long discussion addressing the status of these open questions. Now, we can discuss about any of these questions, of course. If you're interested later, you can check out the paper. But of course, I had to make a choice on the presentation, so I'm only going to discuss a subset of things. What happened? I disconnected from Zoom.
Zoom is like.
I'm not.
He's still connected to the internet.
Yeah.
Facts.
I'm not sure.
I have no one who reply that was
There's a correlation.
The communist
Yeah, I don't know.
But turn off the Wi-Fi and bring it on again.
Well, now it's not okay.
yeah.
Okay. Okay, we're back online. So then I'm going to choose a subject with these questions and discuss, but of course, feel free to solve me. And if you see some questions that I ignored, to know more about it, we can talk about it. So, the first point, we're talking about non-singular paradigm. The first point is, of course, what does it mean to be non-singular? And with my surprise, there was no agreement during the workshop, which is something that kind of surprised me. But I would say that we can require to we can call non-singular something a theory in which we have some completeness of physical trajectories. So, genetic completeness, which means that a predicted theory should not contain undoubted entities of physical trajectories. and also fitness of physical observables. So we want quantities that we can measure to remain finite, and this is for instance of conversion invariance and so on. But of course, I mean, these are the requirements that I'm going to ask today, but you could have something different. You can ask, for instance, some people will drop finities of physical observables as long as the theory is well behaved that you can predict the fate of an observer. I mean, there are discussions, but I would say this is reasonable. Yeah. Yes.
So, for example,
both they would focus on the models where at least in principle both of them apply. So I would try to be kind of generic in the discussion that we're going to have. So it could be that some specific model, some of them will actually not be there, not be applicable, but the goal would be to have both of them. But we can like when we see specific example. And yes, I mean, this is just a cartoon of an object that we can obtain. There is a more precise classification that we can do, but this is just a simple representation. We have here just classical black holes in which we have an horizon, and within the horizon we have a singularity, which is not the same as the black hole. It's not the point in space, but it's just a cartoon. One simple regularization of these objects, like regular black holes, in which we just replace the singularity with a regular core, and this core must be shipped within an extra inner horizon. And then we have something more extreme, in which we have an object which is horizonless, so there is no outer horizon, and we have some surface of the object, some boundary of this object, but there is no horizon in the space time. And I want to discuss the caveat, because another question in the day of discussion was whether or not we should even expect a theory to produce non-singular spacetime, whether we should expect in particular geometric dynamic theory to produce non-singular spacetime. Because, I mean, of course, what is usually done in the research or in the people studying this topic, and also is that an implicit assumption that we can use the tools of differential geometry to describe the problem, but in principle, this might not be the case. And there are at least two possible caveats. The first one is that if you just start to take a theory that goes beyond general relativity, maybe inspired by quantum gravity, maybe it's just some phenomenological model or something like this. This theory might produce non-singular spacetime for reasonable initial data, but there may be still some singular solutions. So, for instance, if we study a vacuum solution of a given theory, and we find that this solution is singular, but we don't know if this is going to be produced dynamically. And I see that very often people study these solutions and it's singular, and so we don't care about the theory. But I mean, this is maybe too fast. We don't know. I mean, the fact that this solution exists doesn't mean that it's produced dynamically. And in particular, if it's a vacuum solution and there is no singularity, I mean, why the spacetime is called not flat, right? So I would expect vacuum solution can be singular. Simply, we need to understand whether this singular solution are produced dynamically. And the second caveat, so maybe more obvious, is that maybe we cannot use multiple differential manifold to describe the fundamental theory of measure. Maybe we need some discrete geometry. Maybe just have a breakdown of the usual tools. But I would argue that still it's interesting to have So we have differential geometry and standard tools, so the kinematical tools of general relativity, and use them as a working tool and then discuss the implications. And maybe at the end we can see what happens. And now let me give some very simple example of non-singular geometry, and then we will build on this, and then we'll show this type of plot of them during the talk. This is a very simple modification. You can see that this geometry is something that says parameter L. We don't switch off this one. We just have a Schwarzschild black hole. And here in this plot, I'm plotting the value. This red line is the outer horizon. This is the inner horizon that I told you it's there when we want to replace singular black hole with non-singular alternatives. Here I have the standard line that is Schwarzschild at the end, and this segment here is a second line segment. Most of you are aware that are there when we have not horizon based object. So, as I said, if this parameter L is equal to 0, we just say Schwarzschild. We have one singular lightning at R equal to n, one lightning at R equal to n. And now we can increase this value parameter from 0 to some non-zero value, and we see that we still have the outer horizon, we still have the lightning, but we also have the inner horizon. And once this parameter exceeds some limiting value, outer inner horizon disappear, but we form a second lightning. And in the rest of the talk, we can consider more involved situation, but I will discuss why this is kind of universal and why I'm focusing on these quantities, especially the inner horizon and the extra lightning. So the second part, which was also the second day of the workshop, was about dynamical formations, the second part of the paper following. I will not discuss this today unless we want to address something that during the discussion part. Just a warning that there is really a lot we don't know on dynamical formations. Most models we don't really have some equations, some dynamical equations. Maybe one exception, boson stars here. Your experts on it. But for most objects, I would say that there is a lot in this direction. What I said I'm going to talk about is instability problem. So imagine that we do form these objects somehow. Again, there is a lot to learn on how to do that. Are these objects stable or not? And I will start studying regular black holes. So the object with outer horizon and inner horizon. So this shaded area here, this simple diagram. Also, for some reason, I start from the static spherical symmetric case, in which I just have this metric here. Now, this is not the most generic one. I'm not going to discuss objects which have a more like topology. This is something I'm not going to talk about today, but it's another possibility. But focus on this case here. So we do not have something like a module, so there is no minimum radius. Yeah, just R squared plus a generic function of R. What are the implications of this model? Now, I mentioned before, we have a given number of horizons. Beside the outer horizon, we have a second one. And this can be seen very quickly, at least in this case, in this simple case. Simply because the horizon condition, as you know, is just this function vanishing. And just by requiring that asymptotically you get asymptotic flatness, and that at the inner horizon, this condition comes here, the inner of the object, when you require absence of conversion invariance singularities. You immediately see that you have a given number of roots. And the simplest case is 2. So we have outer and inner horizon. And in particular, the quantity that is relevant for us is the surface gravity. We have several definitions of gravity. For us, this one is it's the one that we are going to need, which is telling us how now the ray either focus or the focus of the outer in the horizon. And in particular, it's what's going to be useful is that the outer and inner horizon of surface gravity that have opposite signs. Now, why is this something that is going to be relevant? Well, I mean, the color structure of this spacetime, this is just the static integral spacetime, is the same as laser nostrum black hole. Now, this is Pedro was asking before whether or not I was going to consider one or two, like the possibility to find the curvature invariance and or JC completeness. I mean, you can see here this spacetime has Cauchy horizons. So there is no curvature invariance, but also the geodesics are incomplete because the inner horizon is also a Cauchy horizon. So if you close this Cauchy horizon, you need to give new initial data to evolve the initial value problem. So this space-time here does not satisfy the requirement I was putting out at the beginning. However, this is just an artifact of considering the static elements. It's later something like this for a long time, but dynamical, and this is not an issue. Anyway, as I mentioned, the colors actually is the same as the red note from the call. And we know in GR that the Cauchy horizon and the inner horizon is unstable, and the nostrum or Kerr black hole. Meaning that small perturbation will produce either another space-like singularity.
How general is that?
In GR, it's, I mean...
In electromagnetic.
What?
You mean in electromagnetic?
Yes.
But
yes.
with the cosmological constant.
So the point when you put the cosmological constant is, I mean, it's about the strong harmonic sensory conjecture, right? It means I mean, the very late time of the perturbation decays faster, and so this might compete with the amplification which you have given instantly, right? If you put much of it. But still you have a huge amplifications, right? So for physical black holes, I would say the role of cosmological constant is not crucial because I mean the cosmological constant will only change the behavior of perturbation after you have enough time to freeze. So the propagation must travel from the outer horizon to the cosmological horizon. So,
Matter-of principle.
yeah. So in Matthew's principle, I completely agree with you. In practice,
Yeah, so in the universe, okay.
Yeah.
But as a matter of
as a
principle,
matter of principle, I agree.
and as you know, there was a big debate about it.
Absolutely, yes.
So what's, in your view, the outcome? Is a positive cosmological constant, is the inner horizon unstable or not?
I would say so. Okay, for sure, in practice, it's unstable and does not change anything. This is my point of view, because you can see that the stability is exponential, and the exponential is in time scale to the surface gravity of the inner horizon, which is very fast. And you can see that after something order for the general star, we need order of magnitude of 1 minute to be like or seconds to be to the Planck scale or even beyond, right? So I would say that 1 second for an external answer. So I would say that in practice you will go to a point where you need quantum gravity way before cosmological constant will have any effect.
So, in terms of gravity, the results that we have is for the fact or so it's not clear what the answer is. So I think there is generally stability, but
On the end state,
it's the production of singularity in outcome.
yeah, no, okay. I mean, what is the end state? I think it's something that we should consider beyond electrovacuum or beyond GR. But whether or not there is an instability, I think this is something that we should know. But it's not influenced by the presence of the cosmological constant. Because
No, that was not my understanding, even because there are technical issues there. When you say that there's a growth, it depends on an asymptotic observer for which there's a time.
Yeah.
Whereas in the sitter, this is debatable because you are no asymptotically killing time like vector field. And so even that was
but
a
if
bit
I
tricky.
compute curvature invariance near the inner, not at the inner horizon.
Yes.
At the inner horizon is something that depends on the causal structure of this method. But near the Cauchy horizon, and then what near means is something we can discuss more in detail later. You will see something grow as you approach the inner horizon, and this growth is very fast. And if you compute the time in which the cosmological constant, I mean the time in the distance you need to be from the horizon, from an influence of the cosmological constant, the curvature invariants are way beyond final level. So I mean, it's not infinite, but it's way in the quantum gravity regime, way before you reach original wave.
Okay, let me ask you then another question. I'm focusing on the positive cosmological constant. I think some people look at people.
No,
Which is fine.
I mean, this is my opinion. Many people don't agree.
But generic. So regular black holes have an inner horizon, as you made the point. Usually the end table in general. So is there any evidence in your view, or what's the
What we're
evidence?
going to discuss in the next
Okay, so how generic is going to be in whatever model we consider?
Yeah, that's exactly what I'm going to discuss in the next.
Okay,
This is what
now
I'm going
I'm
to
anticipating your-
But this is a very good point. And the point is, we want to do the same, but of course, there's a big problem. We don't know the field equation. Right? We were talking about electrovacuum or the cosmological constant. You can say it's something geometrical, but we're talking electrovacuum when we talk about if we want to produce a singularity. We don't know the field equation generically. We can take a specific model, we can take the field equation, but if it's still an open problem GR, what's the chances that we can do this for any model that give us the one back home? So this is a huge problem. What I want to argue is that we can take some lesson purely from a geometrical point of view, but I want to be very clear that there are limitations and there are assumptions, and this is what I want to discuss now. What are the assumptions and what are the limitations? Because otherwise it's not magic. If we can do something only geometrically and we can discuss instability geometrically, that would be magic. Just there are some assumptions and there are some limitations. And we approach the problem in a similar way to what we were discussing, for example, and also just simplified settings. So we have this, people are not maybe familiar with what's in GR, we just take background space-time, which we take for in this case a regular black hole, and we add some perturbation. Now there are different types of perturbation that we can consider, but we start on the simplest possible case, which is just two nutshells made of dust, so there is no pressure in the shell. So we take this shell, like 3, I don't know if you can hit the level, and 4, one outgoing, one ingoing on shell. They will meet in the two surfaces, like in radius R0, and then they will produce two parallel shells, one and two. And so you get the space-time divided in this full region, and you can use the first junction condition to put some relation on some quantities of the space-time in the different regions. But this is purely geometrical. There are some assumptions that at the place where the shell meets, you don't have any singularity worse than the fact that you have a shell, which is a singular stress tension. It's kinetic energy, but zero width. But it's just geometrical here. It's just the continuity of induced metric of the shell. And if you take the nostrum, Schwarzschild is M of R just a constant. So if we take the nostrum, we will have also contribution from the electric charge. This can be a generic function here. So this is completely generic. And And we get some relation that connects this mass function, this linear shock mass function in the region A, which is the region in between the two shells, with respect to other parameters. Now, given that we don't know the field equations, we don't know the theory that give us this result, because we don't even have a precise physical interpretation of this mass function. I call it mass because in function is just constant, just the asymptotic mass. But what's important is that this parameter directly enters in the curvature invariance. So the curvature invariance are going to be proportional to this parameter, depending on what you choose. For example, the Kretschmann scalar, I don't know exactly how to tell, but it would be this m squared something. So if this diverge, also the curvature invariance will diverge. And I have here the quantities, m in and m out, which is just the jump of this function across one single shell, which again, in GR, we know it's just the energy of the shell. The energy of the shell with which will increase the local mass inside and outside, just because we have built here, but it's very symmetric. We use the junction condition, and the jump is just given by the energy of the shell. Yeah, we don't know what is this jump. Before, we just plug these shells near the in our background space-time, which is our record, and then we will also move this crossing point closer and closer to the linear rise. Now here we don't really know what is this jump, and here is actually the assumption of the analysis is that we assume that the asymptotic mass that we can measure for this geometry will have asymptotic or reduced version. The asymptotic mass is shifted by a quantity which is proportional to the energy of the shells. Now this is an assumption because it would be that gravity completely switches off, and so inside and outside the shell the geometry is completely unchanged. But this is quite reasonable. So if I throw a shell, an asymptotic observer will see something that it's asymptotic mass difference from something proportional to the energy of the shell. So this is something which is, kind of taking something from the dynamics of GR, this old story GR, and we are using it. And this is the assumption. It is, in my opinion, I mean, we can discuss whether or not it's a strong assumption, whether or not it's like the result is even here, but this is the only assumption that this is why I want it to be very, I gave it a few tests because I wanted to be clear on what is the assumption of the analysis. And then the rest is just algebra. And here I have discarded the closure that I anticipated the question because modular constant will only be relevant at very late times. And when you put all this together, you get the initial mass, you just get it's basically the same result of the GR, grows exponentially. But now, all I can say is that as more perturbation is a huge arch back reaction of the geometry. I cannot go beyond this. This is the limitation of the analysis. I can say that this is quite generic, but you cannot prove what is going to be the end state. And we have some consideration, but there is no way of knowing what is going to be the end state of the geometry. You can just say that this level they call space-time, which are apparently a very simple and easy solution of this problem, it's not so simple and easy because they are generic and stable. And then once you produce them in some given model, maybe a toy model inspired by quantum gravity, you should understand what's going to happen as a result of the back reaction. But what you can show generically is that this is going to be large. It's going to be amplified. And this is really geometrical. Yeah, we can repeat the analysis. I will not go through this by changing the setup Instead of two null shells, we can have one null shell and one continuous flux of energy. Some people are also down to just two fluxes of energy. But this doesn't change much because what you see generically is that you have some time in which for any regular black hole geometry, you can generic, for any regular black hole geometry, you have an exponential build-up of this curvature invariance for some given long time. After this time, it depends whether you have a cosmological constant, it depends on the geometry, and it could be something that's close polynomially or something like that. But you have a long time in which this is you have an exponential growth. And you can also compute what is the final local energy compared to the initial one, or local value of this curvature invariance. And you can always see that it's a huge back reaction. So I don't have the formula here, maybe I should have it, but you always have a very large back reaction. So this is all I'm saying, that a small perturbation is a huge back reaction. Yeah, sorry. Yeah, because I skipped something. This is but this new is actually just you cannot be when you use the equation is just advanced time. It should be P. It's just the advanced time. So this is the time for and P is just the decay of the perturbation. I mean, yeah, I just showing for some polynomial decay, but you can have whatever type of decay because again, this is not something that this is not something that only folks. It's only at late time where you have this growth at every time. So actually, this can be seen much clearer here because we have repeated the analysis, but instead of focusing on eternal record, we are just giving a geometry which is formed in one time as an effect of gravitational collapse, and also disappears in one time. Maybe evaporation, or maybe some evaporation, or maybe some other effect. So we just prescribe some geometry, and you can see that the causal structure is extremely different. Now we no longer have Cauchy horizons, so you do have inner horizons, but these are not boundary of the region space-time where the initial volume problem is well defined.
Sorry, I think there was also a question online by Hector. I don't know if you still have your question, Hector.
Yes, sorry for interrupting. So my question was regarding the previous slide where you showed these numerical results for the Hayward and the Bardeen metric. So yeah. I was probably you said it, but maybe I didn't understood. But I was wondering which kind of matter did you use to produce these simulations, because well, you need to close the system, no, in some way, and have the matter for this.
Yeah. So this I was just having one null shell, this divided by sigma in this here, and then a continuous flux of energy. It's just if you see the equation, maybe you see the point. Yeah, here you have ideal space-time, this M of B and R, and they just have a flux of energy going in.
I see.
Just expressionless dust. Basically, also the null shell does not have any pressure. It's just a thin shell given energy density.
Right. So it's just a proxy for whatever matter can be there.
Yeah.
No, just a matter shell.
I mean, this is. I mean, you can have. There are several models, and in all of these models, you have some assumption that you cannot really justify because you take some aspects from the dynamics of GR. And I explained in the previous one where you had only two null shells what was the assumption there. Here you have something a little different, but they all have the same qualitative result, which is that you have this type of exponential growth of perturbation for a very long time, and then maybe you can have something different. But for a very long time,
I see.
and this is something generic because it's just how the perturbations are amplified at the inner horizon by geometrical features.
Okay, thank you.
So as I was saying, why this also is related to the issue of the epistemological constant, why I think that this is not as a matter of particular relevant is because, again, I stop once we show that there is a large reaction. Here, the causal structure is very different from the iris and the string or the diagonal space-time. We just write down the geometry by hand again, it's not dynamical. We just prescribe something that forms a trapped surface and closes the trapped surface. So this region here is the trapped surface. We have outer in the horizon. And then the merge and disappear in some final path, which can be very large. And again, we have the same type of perturbation. Again, I will skip the details. But yeah, again, I'm plotting this is R, this is the advanced time V, this is the inner horizon, and this is the outer horizon in blue. And yeah, the trapped region is what is in between, lasts only for a finite amount of time, which is usually very large.
So what determines that large?
In this model, just the gods decide. Generically, it would be like, I don't know, what is the formation, we just make a repetition columns. What is causing the operation if this is of gradation, it will be order n cubed. Gradation. At the end of the operation, I don't know what we do, but this is the order of magnitude, or if you some other fast process, I don't know, it's going to be faster. In this case, we don't worry about that. We just playing with the model.
Without knowing where the parameters are coming from, speculate this could be a non-linked astrology. Yes. So during that time, the phenomenology of this model will imitate that of a black hole.
It will definitely imitate very, very closely. But what they also said, okay, this development could be very large, but they also said the instability is going to be very fast. This is the results that they wanted to give. But although, again, I don't know what is going to be the end state. So one thing that could drive the instability could drive the evolution of this object. Exactly this instability. Because something must happen. Or something will probably happen at the same time. But so the instability, the time scale of the instability is related to the surface gravity, which in most models is Planckian, so it's going to be Planck time, extremely fast. And these are measures for like in terms of this asymptotic coordinate speed, so it's not going to be saved. Most models are going to be saved by just redshift.
So I'm a bit confused. You're saying it can be very long-lived, but then the stability is very fast.
Exactly. This is what I mean. The conclusion is just that this model has to simplify it. So because we take something which is very long-lived, but we find an instability very quickly. But to understand what is the end point of this stability, we need the field equation. So we can prove that the instability geometrically, and this I think is very powerful. With some minimal assumptions. But understanding what is the endpoint, this is something dynamical. You cannot do that geometrically. So this is exactly the contradiction is exactly what we want to highlight. This model of a very long-lived reverberant core is not a good model, or at least it's too simplified. You need to understand how to tell the instability.
So when you're saying it's very long-lived, but it's already being afflicted by the instability.
Yeah, so okay,
so it's already not non-stationary in the sense it's evolving towards something we don't know what it is.
We start with a mass function of this sort, in which we just have a mass and then a perturbation of this mass that is going to trigger the instability. And then we have this function here, which we put by hand, which is telling you when this is forming and when this is evaporating. And this we put by hand. This can be very wrong. We are choosing the model. It's not coming from any equations. We are choosing. Now, on this model, we have the perturbation, and we see that there's a very, very fast instability. So this model originally was just too simple. We need to replace it for something else. something could be that well, I'm keeping it aside, but I'm not going to be able to finish the talk. Something could be that this stability could drive the inner horizon, move it, and maybe the track region will disappear in a short time. And that would be amazing because it will give us some possible observational feature that we can move on. That would be my favorite option, of course. That would be great. Something else, I said this is driven by the value of the surface gravity. Something else that can happen is that this ability will push the value of the surface gravity down. And you're studying what happens when the surface gravity is very small, is zero. We've written down some geometry with zero surface gravity, and they say that these are stable. And now, can we form them dynamically? And this is some way that this could be formed. So these are two of the options. The third one is the inner horizon moving around. So the depression will not be able to accumulate there because it will oscillate between the small value and the outer horizon. So we will not be a growth of perturbation because of that. It will be probably the worst model from us because we will not see anything outside, or at least very small inside. But this is also a possibility. But yeah, I think it's very powerful that geometrically we can say, no, this model will suffer from something. And geometrically we cannot say what is going to be there. But there is some non-trivial things going on. And then we have possible speculation of what can happen or whatever, but it's going to be there. So yeah, this is just to say this is very fast and also offers these objects that are finite lifetime. And so this is why I think that the commercial concept would not enter because here this but everything is local. There is no real question. Local physics. Something like it's changing global pictures this time, but we need a very long time to see that. And here this is very fast. So we can also discuss the case of GR later, but actually it will be very easy to discuss it. But this is at least here where there are more limitations. And yeah, okay, I need to select some stuff to cancel. Okay, so we've seen that as this again simplified, I mean, this simple model we had, we have discussed what happened for regular black holes where you have two horizons, and okay, let's take this regularization parameter over this maximum value. We get something which is horizonless. They can still be very compact, so you can still pass all the current test. At least I don't know if this model will pass it. Some other models will definitely pass it because it can be very compact. Is this going to be simply, I mean, a simple solution with no issues? And I mean, you all know the answer, and here we'll go very fast because this is about the light ring instabilities, but I feel that I mean, this audience you probably all know. But the point, just to be quick here and move on, is that we can instead of focus on this X-ray horizon that is not going to be there, we need to focus on light rings, which corresponds to this location of the circular orbits. And in the kernel of space-time, we only have one rotation side, which is a saddle point of this expected potential we can introduce here. And in the words of sound view here, you have shown that you will have at least a second light ring as soon as you add as soon as you remove the presence of the outer horizon. Okay? And there is a topological here we can have in the light ring we can find we can saddle points of this effective potential. And if we don't change how this potential goes to infinity and the radial coordinate, and how they go to the center of when you approach the center of the object, which is dictated by regularity. This is not very flat, and this is regularity of the space-time. Then you can see that you will create saddle points or extrema in pairs. This is for the one-dimensional projection of the potential, but this is a two-dimensional effective potential because it depends on the radial coordinate and the theta coordinate. And the outer light ring is what is useful for the phenomenology of the space-time. And inner light ring can be dangerous because you can see here it's a minimal effective potential, and so in some rays where perturbation will accumulate, maybe lead to some other sort of instability. But I think it is what I want to discuss this. And yeah, I just wanted to mention the result that the fact that in this picture, the inner light ring is a minimal point of the potential is actually quite generic. In the initial work, it was proved using the null energy condition. And actually, you can also prove it removing the null energy condition, but just making the extra assumption of the shape of the potential and the standard light. And you can actually combine these two results. I was discussing in Frankfurt with Luciano and so on. We were discussing about some model in which they had some ultra-compact object, and the model was such that you had violation of the null energy condition almost everywhere inside the object, but there was a short band where the null energy condition was satisfied. And they were computing the light rings, and they were surprised the light rings were always inertial. But this actually must be expected because it must be a minimum, because they had exactly general expansion outside. And where it's a minimum, it must be where the null energy condition is satisfied. So you can also combine these two results. Something else. Of course, that was fake symmetric, so it was kind of, this let's say, this addition that I give here, it was triggered because it was fake symmetric, but also in more generic cases there. But this is just to say that you will definitely have an inner light ring, which is a minimal effective potential, and can be another source of instability. And so, if you look back at the diagram that I was showing before, this is just a little nicer diagram, but it's the same. You see that we have some region here where you have an inner light ring, which gives you an instability. As soon as you go beyond this point, you will have an inner light ring which seems to give you instability. And if you go too much beyond, you will not reproduce the phenomenology. So it seems that you are doomed. And also in the point here in the middle, you will have an extreme horizon. And there are also arguments and also there are instabilities. So the question is whether or not there is no hope. And I would like to argue that no, it's just that there is a lot of work. Yeah. Because there's the yes. By the issue of like mass information stability, as I discussed, there are limitations in there. We don't really know what the question the endpoint. I mentioned that there are some regular black hole without instabilities, but we don't know if we will follow them. So we don't know if this is. So I would say it's understood. When I say quite well understood, I mean it's understood what are the limitations of the analysis and what is the open room to. And one thing I would say, at least in my opinion, and don't get mad, I would say this is not very well understood because we have some heuristic argument for the general case. What I'm saying, you trap perturbation there. This will linearly attract more perturbation. The potential will get deeper and deeper. I think the last paper by Pedro. But this is, something that I would say would need a bit more thinking to understand how solid it is. And we have some numerical evidence, but only for some specific. And for extremal black hole, again, I didn't go into that, but also there is some understanding, but at least in my point of view, I mean, at least I don't understand a lot of these things. I didn't discuss that, but again, so this is not to say that the hope is doomed, because everything you do is going to be unstable and nothing can reproduce a viable model. But to say that there are issues, anything that you consider is going to be problematic, but we need to, we know what to need to do to understand, why we need to look for things. And I wanted to go to observation signatures, but I don't know how much time I have, none probably, so I can skip it.
See.
Okay, 5 minutes. Okay, so I'm trying to restrict the time workflow.
I mean, it is a bit more than that.
Okay, this is, I'm very happy to hear this one.
You had some questions in the meantime also.
Okay,
Don't feel too much pressure.
great.
Just do the 20.
Okay, so again, there were several questions asked and we're discussing. I just want to talk a little bit about what are the different observational channels that we can use. First, fast answer, if we have 20 seconds, gravitational waves, waves like telescope. But I want to go a little bit deeper in one aspect, which is what I wrote here, thermal emission due to accretion. I want to explain what it is, because there is something interesting there. And also because I say that I was, the question are generic, but I focus on my work. And there is why I want to go there. So what is the thermal emission due to accretion? Is the fact that, I mean, black holes are not in vacuum, and especially if you look at Sagittarius star, we have a flux of energy going to the black hole. And if instead of a black hole, we have something which is compact, very compact, but there's some boundary, some surface, or the horizon of the object, we might expect an outgoing flux of energy. And we don't see this outgoing flux of energy, so we can say there is no object, this object does not have any surface. And I mean, the argument is, we can done much more detailed than this, than we do better, but it is a very interesting argument, first put forward here. But there are several points that needs to be taken into consideration. First of all, is that strong density is going to play an important role. So if you have something which is ultra compact, you have some matter accreting this object, hitting the surface, and then being emitted, which was in how the original model was discussed. Then you need to take into account that most of the things emitted will go back onto the surface of the object, because in order to escape, they must be emitted in a very thin emission angle. That the limit of this compactness going to the black hole limit is just radial emission. And if you do this, you realize that each photon must bounce on the surface many times before actually emitting. So the time scale that you need to wait before getting a flux of energy back, it's much longer than what you would maybe expect. And this is telling you that it's something extremely compact. You will not see this flux of energy at all. So you can put a bound on this compactness parameter, mu, given here, which is 0 for black holes and non-zero for any other object. But you cannot rule out anything. This is extremely compact objects that you can rule out. Still, you have some models that will survive. However, I mean, like when I was studying this paper, you realize, okay, you have to I mean, these photons will bounce on the object several times. This is what I told you. And especially for this value here, it will bounce on the object 10 to the 18 times. And so you realize even if there is an extremely tiny absorption, it's not going to be one, like a black hole will absorb everything, but it makes a tiny absorption collision. Maybe you will not see anything. So you can just repeat the analysis by considering that there is an absorption parameter, kappa. So the object that is not a perfect absorber like a black hole, but it's not even a perfect mirror. It's something in between. And then you can study the constraint that it gets in this case. And you can see that the constraint gets extremely weaker. And in particular, if you have something which, I don't know, you expect a social coefficient of 10%, the constraint is basically not there. I mean, even like basically any object on the fine this constraint. So unfortunately, yes, there is this channel, but it's way more difficult to rule out this possibility than you would expect naively. I hope I was into the 5 minutes because I can just. And the last question I wanted to discuss was whether or not you can distinguish issues of new physics with astrophysical uncertainties. But I was not going to say much about it, so I can skip. Just this is a very difficult problem because maybe we see some deviation from GR, but we don't know if it's due to new physics or to astrophysics, and not take into account. I will just stop here. And just to say, I mean, I said many times, there's still a lot of work to do. Hope I convinced you that this is interesting, and there's still a lot of work to do. But also, I don't want you to take this pessimistically. I said that there is instability basically everywhere. I think this is a positive feature because observations are very difficult, and if every possibility was safe, then we could do anything and we never see. We will never know how to address the problem. It seems that, yes, observations are very difficult, but we will have a lot of data in the future. And most solutions are problematic. So, I mean, we need to combine theoretical studies that will really tell us where to focus our attention, because most possibilities are going to be pathological from some sense or some other. And theoretical analysis will tell us where to look. About those classes, some of them will not have any difference from black holes, but some of them might. And so I would say that the fact that there's issues is very positive because it's telling us where to put focus. And I finish here with the full list of questions. Yeah, thank you.
Hi, thank you for the call. So regarding this that you mentioned, were there any people coming from the quantum gravity community? And if so, what are their opinions regarding these attempts to fix the singularity issue just from a geometrical?
There were people coming, so I can show you the list. I mean, we invited also others, these were the ones who came. On the gravity community, there were people especially working on hydraulic safety. They looked more open. There was Alfio, Banana, so there were people, people from everybody else, string theory people and loop people. They all didn't come, so they maybe have a different point of view. But no, they were open, and of course, it's not just to say that you only study this mood manifold and you say this is the full story. Okay, we imagine that we need to go beyond at some point, but can we still learn some lessons from these models? I mean, these are definitely simplified models, but can we learn some lessons? For example, in quantum gravity, there are all these models that you have this bounce from you have collapsing object that expand into white hole. And in those models, you really have some regional space-time where the geometry is not well defined. But it has more regional space-time. And so we can still analyze the tools that I described here. So, probably, yes, from quantum gravity point of view, you don't expect that this is going to be enough, but this is going to give you some information.
But would you say that the people are talking to each other, so you gain from their insights also?
I mean, this workshop, yes, not as much as we should, but yeah, it happens. I mean, there are discussions. Maybe we'll discuss it yesterday. Right? We should discuss more, but no, because there is something.
You need to find the right friendly person on the side of the document.
Also, Hector has a question, so please.
Yes. Hi. Well, first of all, thank you very much for the nice talk. Well, first I have one comment that is that regarding the model of thermal emission as a means to rule out some of these models. So maybe I should put my video because I feel strange. Right. So, well, I just wanted to comment that there is another way to overcome it. That is when if there is no surface on which the fluid can crash, the energy of the fluid may not be released, at least not at that moment, and can be affected with the flow. In that way, it can be so radiation can be emitted very slowly, and this is another way of masking these horizonless compact objects. No?
I completely agree. I mean, I was very fast here. I was just describing what is, I think, the most. I mean, the biggest effect is coming from this absorption coefficient, because it can also be as small as 10 to the minus 5, and it will change the constraints by 10 order of magnitude. You know, so
right.
this is, I think, in my opinion, this is the biggest effect. But if you look at this in the last paper, we have something which is more generic. We didn't choose any specific model, but we also discussed the possibility that instead of having immediate emission, the radiation is absorbed for some time, which will give like some free parameter, and then re-emitted. And this would be exactly the case that you were discussing. And
right.
This also goes beyond the, I mean, overcomes this observation if this time is long enough. But
exactly, and then one can not require to have extreme redshift, not to have to mask this. So I have other questions. I don't know if I am allowed to do more questions, or if there is anyone else that would like to.
Yeah, you are allowed.
Yes. Okay. So the other question that I had, is that. So I find very interesting all of these issues of singularities in general relativity, but unfortunately I am a bit unfamiliar with the way in which this is treated normally. And when I think of this, I many times think that, for example, in the theory of hydrodynamics, it is very usual to produce singularities, no, from very reasonable initial conditions as well. But something that we have in the theory of hydrodynamics that allows us to deal with them is that we have a weak formulation of the theory that can be understood, let's say, as an integral formulation. And this allows to at least solve conservation laws in the neighborhood of the singularity, and and predict what happens after a singularity is formed, or evolve a solution that contains a discontinuity. So I was wondering, is there anything similar for the case of general relativity, or something to prevent us from doing a similar approach?
Well, I would not know how to do the similar approach that But no, this is very interesting. When at the beginning I was saying what you want to give to the model, then I was also talking about cleanness of curvature invariance. Then you may want to say, okay, I can get rid of this, and you can allow for something which is intractable singularities. So you do have something which is infinite. Some quantities will diverge, but you can, I mean, geodesics can go through and you can understand what's going on the other side. So maybe that would be something similar. But there are a lot of issues there because generically, some observer will be able to go through, but not all observers. Like this is something that happens. Yeah, it's something that can be, they should be understood case by case. But I would like to understand more what is done in the fluid dynamics. So I don't really know. I'm not really familiar.
Just for maybe comment, yeah, agrees that fields are linearly degenerate. That's a word may not be the salaries you don't develop this continuity. And that's not the basic hydrodynamics. I am not another the thing is here prevent. I mean, that's why when we solve these equations we don't expect to appear in the
Oh, but you can get some similarity that integrates beyond this similarity. Something increase or happen. Yeah, I mean, I don't know if it is the same, but it could be. I don't really know what I mean the case in hydrodynamics, but there could be something there. Yes.
I see. So there can be things to explore, and this makes me think of another question that is, so whether there is any insight from these analog black hole models that try to produce acoustic black holes on what happens in the interior of these black holes, for instance, on this issue of the stability or instability of the Cauchy horizon.
This is a very interesting point. So in our analog black holes, you can still have outer and inner horizon, and it's not clear if the inner horizon is actually stable because there are some indication. Even in experiments, it kind of moves around. But this analysis that I was doing here will not apply. It's for a reason that I was discussing that you need to do some assumption on how the perturbation back react on the geometry. And then it's usually minimal. So I was just saying the mass function changes. But in acoustic spacetime, you can reproduce the background geometry, your perturbation travel on this geometry. Like if travel on this the perturbation propagates on this acoustic medium, like if it was in a black hole geometry. But there is no back reaction, so the geometry is fixed by the experimental apparatus, and the perturbation do not change because there is no dynamics. It's purely kinematic.
I see.
And so there is no instability simply because the geometry is, the perturbation is invisible to the geometry. The geometry doesn't change at all. So
I see.
Cannot apply this because the geometry cannot be changed by the perturbation. It's not fixed by the experimental apparatus.
Okay, I see. Okay, well, thank you very much.
Thank you for the questions.
Any very quick question? Well, so if not, let's thank Francesco for coming.